Now, in most problems, before you attempt to solve the problem, what you will want to do is to simplify these equations. And so here, everything we've discussed now is very general. So the only assumptions we did from going to here to there is that we assume a material to be a fluid and not a solid. And then we assume that it was a non-Newtonian fluid, and we assume the flow to be incompressible. Those are the only three assumptions that we did, okay? Now, in most cases, you want to assume a bit more. So anytime you want to step outside of this, so this is anytime you want to step outside, what do you need to do? You need to do a dimensional analysis or a scaling analysis. Right? So this is really key to this class. And sometimes it's just mental, but you need to have a mental exercise of, okay, especially what is the Reynolds number? Because a lot of what we followed sort of Reynolds number lines. Right? But even when you're looking at an interface, gravity waves, for instance, well, what is the Weber number? Is surface tension important, or is the wave, is inertia so much larger than the wave, than in the wave propagation I can probably neglect the effect of surface tension? Right? So every time you want to solve a real problem and you want to now take some of these equations and try and solve that, usually you want to go through the filter of dimensional analysis. So let me write that. So before going outside, you want to go through the filter of dimensional or scaling analysis. Now I didn't make a big distinction between dimensional analysis and scaling analysis. Dimensional analysis, you can always use the Buckingham-Pi theorem. But the Buckingham-Pi theorem applied completely randomly usually it may not help you. A scaling analysis is when you start putting a bit of physical intuition, about what are actually the relevant parameters. Some parameters are not relevant in many cases. Some parameters are not relevant, and if you start adding parameters, then you start adding the non-dimensional numbers, and you can have non-dimensional numbers which are completely irrelevant. Right? So then it looks like the problem is very complicated, but in reality it's not. So there are important non-dimensional numbers that you want to know. Of course, the Reynolds number. This is number one. We discussed the Strouhal number. We discussed the Froude number. The capillary number, the bond number. I don't know. I think those are pretty much those that we discussed in class. And then you need to be sort of comfortable doing a scaling analysis. I would definitely have all of these numbers in my cheat sheet, in my many cheat sheets. Since you have 10 pages, since you negotiated 10 pages, both sided, two-sided, that's 20 pages. You can put a lot on that. So definitely put the formulas for all of those non-dimensional numbers. Also put on your cheat sheet just physical parameters, density of water, viscosity of water, density of air, viscosity of air, viscosity of honey. Just the ones that you think might be viscosity of oil, say. Just things that allow you to compute those numbers quickly. Like an oil-water interfacial tension or water-air interfacial tensions. Those are numbers I would definitely put on my cheat sheet. Like densities, some densities are very common fluids, air, water, oil, viscosity as well, and surface tensions. And the reason why is that, of course, if I ask you what is the value of this number, then I will give you the parameter. Right? I don't expect you to know that. But if you're stuck at some point in the problem, you're like, well, what assumption would I need to do? Then you might want to compute for yourself what the Reynolds number is or what the Weber number is. Or you want to show that that you understand the problem. So let's compute the Weber number. This is what I get. This is high. I can neglect the effect of surface tension. Right? Sometimes it will help you to be able to compute those numbers because it allows you to sort of make the right assumptions in the problem. Okay, dimensional analysis. And then the important one, of course, I'm going to put here on the bottom, is the Reynolds number. this one, this one by now I think you really fully understand. It represents the ratio of, you can interpret it as the ratio of inertial forces to viscous forces. So when it's large, inertial forces dominate. When it's very, very small, viscous forces dominate. But the reason why it's important, because it really often just fixes the solution methods. So the first things that we discussed after, the first kind of flows we discussed after the at the beginning of coil 2 were usually assumptions you can make when the Reynolds number is high, and that you can assume viscosity effect, viscosity to be negligible. So when viscosity is negligible, the first thing that you would do is you just look at the Navier-Stokes equation and you cross out the viscous term, and then you wind up with the Euler's equation. And Euler's equation are the most general way of solving the fluid flow and the pressure field, the flow velocity fields are in the pressure field. So that would be Euler's equation. Note that you still have, of course, to solve, to solve for this field, the flow velocity and the pressure field. You still need to make a statement about Newton's second law. You still need to make a write the momentum equation and mass conservation equation. Both are still important. You still need both. Okay, so then we branch it. So then it becomes a bit more complicated. At this point, there are two things that can happen. Number one, I'll put it here. So to come out of this here, let's say you don't know that the flow is irrotational. So the flow might be rotational. This is the vorticity vector equal to the cross product of u. If you don't know that the flow is irrotational and the flow is steady, then you have the weak form of the Bernoulli equation, the one that you can only apply if you're following a streamline. Okay, so here you get Bernoulli. The weaker form, I'll say. And so this is that your pressure plus 1/2 rho times the norm of the velocity, squared, plus your force potential is equal to a constant along a streamline. Oh, sorry. Now that I write this, I realize I forgot something in the review. So let me go to the previous page. There's one more concept which we discussed right here. One more little things. Do you remember where it was? What comes directly from the compressibility condition? Something which you can use. It's a stream function. No, the potential comes from, this is for later. Yeah, exactly. So it will be the stream function. And when the flow is incompressible, then if you have a 2D flow, a 2D planar flow, then you can write everything in terms of stream function. Right? And we also defined a Stokes stream function for two-dimensional axisymmetric flows. And oftentimes it comes out because if the flow is 2D, then you know that this relationship essentially links u and v, because partial v over partial x is equal to partial v over partial y, and so you can solve, instead of solving for u and for v, you can just solve for the stream function and then reduce what u and v is. So here there was another little concept box which I discussed. The stream function. Okay, now back here, so along a streamline. Now the second this is where the map becomes messy, so I don't want to get lost in my own concept map. So the second one is when the flow is irrotational. So the flow here is irrotational. Then you can write that, then you see that the momentum equation in the Euler's equation, you can rewrite it as the unsteady Bernoulli equation. Which is a much stronger form of the Bernoulli equation. And that is rho d, well, okay, let me actually back off. Before I write that, let me here remind you that when the flow is incompressible, then in that case, if it's irrotational and incompressible, then we are in the realm of ideal flows. Right? So it's incompressible, therefore the flow velocity field, it's irrotational, therefore the velocity field derives more potential, right? And we're assuming it's incompressible, therefore divergence of u is equal to 0, right? Which means that the Laplacian of phi is equal to 0. So we have the flow field, the flow velocity field derives from a potential, and that potential is a harmonic function. It satisfies the Laplace equation. And that is convenient because analytically we know a lot of solutions to the Laplace equation. Okay? So that is true, and this potential, and you can write the unsteady Bernoulli equation. That is partial phi over partial t plus 1/2 rho times the velocity squared. Remember, you're writing this in the bulk. So this velocity here, you could also write this term 1/2 of rho grad phi squared. It's the same thing. Plus the pressure plus your potential, force potential, is equal to a function. Now that function might depend on time, but it does not depend on your streamline. It does not depend on space. So in particular, if you have a steady, in particular, you know, a sub equation would be here for steady flows. You would have something which looks exactly like the other Bernoulli equation, except this constant here is independent on the streamline. Alright, so it's the same everywhere throughout the fluid. Okay? So those are the two important equations. Here, study Bernoulli equation. And here, the stronger form of the Bernoulli equation, only if the flow is irrotational. Okay, I forgot something, so I have to go back here. Here, this is along a streamline. Right now, in both cases, in this case here, it's unnecessary because the constant is independent on the streamline. So the equation is still valid though. But here, especially when the vorticity is not equal to 0, you don't know if the flow is irrotational. Usually, you want to make use of the Bernoulli equation plus when you write the Euler's equation in streamwise coordinates, right? Then you can also project it in the direction normal to the stream to the streamline, right? And that gives you an information about how the pressure varies across streamlines. Remember, this is the equation becomes partial P over partial N is equal to rho U squared divided by the radius of curvature of the streamline. You know, how fast the flow, how the flow changes direction. Okay, and I remember the sign. If you have a flow that is bending in this direction, for instance, right, and you're thinking, how does you know that along a streamline you can impose Bernoulli equation in that particular case. But if you want to know how the pressure varies across streamlines, how do you know where the pressure is higher? Is it higher on the top or higher here? On the top, right? So you know here, but the pressure would be higher here and would be slightly lower here. That's because the flow is bent. You need in the fluid, you need a difference in pressure, a difference in force to change the momentum or change the direction of the flow. If the flow is bended this way, that means that you have a piece of mass that is moving towards the bottom. So the momentum is changing, the direction of the momentum is changing, and the direction of the momentum is only changing. It just feels a net force in this direction. So that means you need to have more pressure here than pressure here. Okay. So always remember that. In particular, and this is something which I've said a few times that you don't want to forget, if your streamlines are linear, what do you know about the pressure? It's constant across streamlines. Right? You always know that. It has to be constant across streamlines. Okay, good. Now, after that, there is a whole section on. So this is here when you have flows. Underneath here, I don't know exactly where to put it now because it's not a different topic, but let me say that it branched out of here. We discuss a number of special solutions. And so let me actually have it branch it out of here. So it's still, all of these equations are still valid. Right? But we discuss particular solution method, particular solutions when we discuss potential flow theory. So I think I have to speed up a bit. Potential flow theory. So remember, this is flow around the cylinder. The concept, this solution you should definitely know. Flow around cylinder and associated concept, that would be lift, Joukowski lift, circulation, we discuss very briefly, we discuss all of the different singularities, sources, sinks, dipoles, irrotational vortices, and all of that. And we discussed a particular solution method. So this is not a concept, it's not a fluid regime in itself. It's just a way of solving for the fluid flow using complex potentials. you know, so in that we discuss flow around in sharp corners. And we briefly ventured in for the flow around a plate. And brief discussion of conformal maps. Okay? So this is what we discussed. And then we move to cases where you have to include the effect of viscosity. So I'm not going to do that in chronological order. But the simplest flow, where you can neglect the effect of viscosity, actually don't have to do necessarily with the Reynolds number. It has to do with the geometry. So when you have unidirectional flows, so flows flowing only in one direction, the velocity vector u is equal to, say, u0, 0, then the inertial term just drops out of the equation. Because you're moving in one direction, you cannot feel the effect of inertia, because you cannot accelerate and you cannot decelerate. Incompressible and unidirectional, actually, the consequence is that essentially you cannot feel the effect of inertia. So Poiseuille flows and Couette flows. Those are the two biggest examples of unidirectional flows that we discussed. You know, I would definitely have those flows on my cheat sheet. Poiseuille flow, you know, the velocity distribution, the average flow, the volumetric flow rate, all of these we derived in class. You know, like a very simple example would be to rederive that, but you know, most likely this is assumed to be known. Right? So you need to know that, you know, and then the friction coefficient associated with a pure Couette flow, we also discussed that. So these you want to know. So here. Now we're discussing throughout here. This is laminar flows. Let me say here. So we discussed laminar flows. We discussed another case where the effect of viscosity are gonna drop out. Also related to both now the Reynolds number and the geometry was lubrication theory. So remember, in lubrication theory, it happens when you have a thin film, so different wave length scale in across the flow and in the flow direction. So across the flow direction, you have a small length scale, and when the Reynolds number, now it depends which Reynolds number you pick, but let's say the Reynolds number based on the longer length scale times h squared divided by L squared. When this is much more than 1, then you're in the lubrication limit. And then the Navier-Stokes equation reduced to 0 equals minus delta px plus mu partial u squared partial y squared plus eventually the body force in the x direction. And across, in the direction across, you have partial minus p over partial y plus f of y, right? And of course, the continuity equation. But usually you don't, you know, you're just solving for u. So those are this is how you, I should have put that in black. It doesn't matter, now it's in green. Those are your lubrication equation. But then there is also a very standard solution method, right, where you rewrite the equation for h, the thickness, the thickness of the film. Right. Where you also integrate u over h to get an equation in q. So you first write the conservation in q, dh over dt plus dq dx is equal to 0. That's a way of rewriting mass, the mass balance, and then you solve for h. So this you should remember that lubrication theory, and then That is just a case where the Reynolds number is really small, and where you just the inertial term just drops out because you are in the Stokes regime, and in that case, the equations are just everything without the inertial term plus F, and those are the Stokes equation. And then we discuss another topic which has to do with what happens in between. How do you connect the fact that fluids do have viscosity, but that somehow many fluids, many flows, you can model as inviscid. And what we realize is that there's a very important concept which lies at the boundary between these two, which are boundary layers. Okay, so they're really at the interface between cases where you this is essentially the pieces, the bits of flow. Just think about the flow on a flat plate, where both effects are important, right, and both meet each other. So the effect of viscosity to allow you to impose a slip boundary condition, meeting the outer layer where you can assume the flow to be inviscid and where it's inertially dominated. So we derived the equations for boundary layers, which are the following. So you have, again, now my wall is in the y equals 0 plane, so the flow is in the x direction. So then you have your inertial term, times rho equals minus grad p dx plus mu second partial of u with respect to y, and in the y direction we just had that minus dp dy was equal to 0. Those are the boundary layer equations, and we discussed one particular solution, which is the Blasius boundary layer, the Blasius problem. And this is when there is no pressure gradient in the x direction in the outer layer, because the pressure is constant in the boundary layer. Right? So you have the flow is not driven by pressure gradient, it's just, you just have a uniform flow flowing on top of a flat plate. When delta p over delta x was not equal to 0, right, we did more of a conceptual discussion about what happens, and we discussed that when the flow decelerate, then you're subject to separation. There was a discussion on separation. Okay, and then finally, and now this is sort of a very broad topic, so it's harder to know exactly where to put, but it's sort of really transverse to all of fluid mechanics. I'm just gonna put it here, and that was instabilities and waves. Right, you have instabilities all across Reynolds number in many different cases, but the ones we discussed were really just at the higher, towards the higher end of Reynolds number, so it was mostly here. We didn't discuss any instabilities which happens when the flow is dominated by viscosity, but you have some, the Safman-Taylor instability, or there are many. The Rayleigh plateau instability, but we discuss here gravity waves, and we discussed the Rayleigh-Taylor instability, and we discussed the Kelling-Helmholtz instability. And so if you zoom out, then this is sort of a review of everything that we discussed in this class. And I have 5 minutes for questions. Yes. Yes, and it will come at the same time as the solution will come. Yeah. Yeah. So you have to ask Koen. He's not here because he's in charge of uploading. So he will upload soon. I told him yesterday that he has the notes, but they were going to be uploaded, but it hasn't happened yet.
Can you upload the formula sheet like as you did from the first quarter?
The formula sheet from last quarter's exam? No.
The formula sheet that will be applicable for this exam.
Oh, it's the same. Yeah. I'm not going to give you the details of the, you'll have the Navier-Stokes equation, right, in cylindrical, in spherical, if it's in spherical, or in Cartesian, those you should know in Cartesian. So you have all kinds of things, but then, which simplifications to do, if it's a boundary layer, or if it's this, you will have to know. So I'm not going to give you all of these. I mean, of course, now you have the concept map. You have 10 pages two-sided. I'm not going to do these for you. Those you have to do yourself. Yeah. Any other question? No? Okay. So some of you, who are the applied physics students here, or who are taking 045, 041? Can you raise your hand a bit higher? Who is taking the 45, 041 version? The 6th credit version. So these guys will give presentation about their project on Tuesday morning. I'll post the schedule on the website. So if you are interested, just you're all welcome to come. It's like a small symposium. They work a little bit on their projects. Some are experimental, so I think some are measuring surface tensions. Some are doing some things with membranes. I'm forgetting. Some are doing experiments on hydraulic jump. Did you do some experiments? Did you take pictures? Okay, so pictures, things that they did themselves. If you want to listen, that would be great. I think that would be nice for them to have a larger audience. That's the first announcement, and the second is that was the last lecture. It was my pleasure to be with you for this one semester. Now, for some of you, I know this is probably the last time you hear about fluid dynamics. You have to take the class anyway, but you realize that fluid dynamics, this is not for you. This is completely fine. I absolutely understand that it's not for everyone, but then there's some of you for which you started and you realize this is just the beginning of fluid mechanics for me, because I want to continue in that field. So if this is you, then of course I really encourage you to just get in touch with people who are doing fluid mechanics work on campus, and there is a lot. There is our lab in mechanical engineering, there are people in civil engineering, there are people in aerospace, there are people in applied physics. So there are many opportunities to get involved. So if you realize that this is really something which interests you, then you're really welcome to just to send emails and get a bit of a feel of the different flavors of fluid mechanics on campus. And if you're interested in a master's project and going more deeper in that, then also for the next curriculums, think there are many classes which you can take after advanced fluid dynamics. You can take turbulence, you can take multi-phase flows. I think in applied physics there are classes which focus more on capillary effects at smaller scales. There are classes on viscous flows in aerodynamics, in the aerospace. So there are many opportunities to now, so this is just what you've seen in that class, and then there's another bubble and just going into more specific topics, whether it's microfluidics or compressible gas dynamics in aerospace. And so I really encourage you to just explore. And with that, I wish you also good luck for the exam. So I'll do the same as what I did last time. So the one day before the exam, I'll send you the front page of the exam. So you already know how many problems there are with the different guidelines. The guidelines are the same. You have your 10 two-sided handwritten notes that you can bring with you in the exam.